Welcome to the third part of the tutorial. I am Ashok Cutkosky, and I will be taking you through the last two parts here. So in the first parts, we saw that stochastic optimization problems can be solved using online linear optimization. So the argument was that the sum of all the suboptimalities can be bounded by this linear expression, which we call the regret. We can use gradient descent to solve this problem actually optimally. If we use the right tuning, we'll get a convergence rate of norm of x star minus x1 times g over root t, where g is a bound on the magnitude of these gradients gt, and x star is, of course, the optimal point. In order to do this, we had to use a learning rate that depends on this unknown value x star. Parameter-free algorithms, on the other hand, contain the same rate without knowing x star, without doing this tuning. They suffer a logarithmic penalty, but these dependencies, it turns out, are tight. Without this extra, oracle knowledge here, you have to suffer the extra log term. So what are we going to talk about next in this session? Here we're going to go beyond this worst case lower bound to build algorithms that are maybe more practical in the sense that they adapt to a structure that is almost certainly going to show up in your problem, right? The real world is rarely worst case, and so we want to be able to identify and take advantage of any sort of non-worst case behavior that our situation has. So we're going to start by building an adaptive parameter-free algorithm, and I'll explain what I mean by that in a minute. And then we're going to use this basic result as kind of a building block to accomplish several other tasks. So we'll show how to do better when x star is sparse. We'll show how to improve when f is smooth, and how to improve when f is strongly convex. And then we'll talk about dependencies on the constant g, which I'm going to suppress for the most of the first three parts of the session, just for simplicity. So we're going to assume that x1 is equal to 0 here also in this section, just to avoid writing x star minus x1 too much, because it sort of clutters up the formula. If you start at some point that's not the origin, you can just shift coordinates and all the results will still hold. All right, so let's talk about the adaptive regret bound, our first goal. This is really going to be a second order regret bound, which looks like the following. So we say the linear regrets can be bounded by norm of x star times the square root of some of the norms of the gradient squared, where here the norm is the 2 norm. If I don't specify explicitly what kind of norm we're talking about, it's always the 2 norm. This is can be thought of as the Adagrad upgrade of the parameter-free bound we saw in the previous section using the KT estimator. So that one had a g times square root of t. Here we have a square root of sum of the gradients squared. Of course, in the worst case, these are the same, but in a non-worst setting, this bound could be quite a bit better. This bound is called second order because it has the squared here. It actually has nothing to do with the Hessian, so it's sort of an unfortunate collision of nomenclature. All right, let's see how to do it in the next few slides. Again, for simplicity, I'm going to assume g is equal to 1. So we're going to use the coin betting strategy. In the previous section, we talked about how this is, you can think of this as a sort of a 1D optimization algorithm that we can easily convert any 1D problem into D dimensions, so it sort of suffices to solve the problem in 1D. The overall approach is to think of each gradient as specifying a outcome of coin flips that are some continuous value. And at each iteration, we're going to earn some money, which is minus g times x. We keep track of our total wealth, which is 1 minus the sum of g times x. And in this setting, the outputs xt can be thought of as sort of a bet, right? If x is very, very large, then we stand to gain or lose more money. So x really is naturally kind of a gamble on what the value is of gt. Analytically, our goal is to make the wealth really big. So if we can make wealth bigger than some arbitrary to be specified function h of the sum of the gradients, then the regrets will be bounded by 1 plus the differential conjugate of h, evaluated at x star. So the interesting thing about this strategy is that sort of steps 1, 2, and 3 don't really reference x star, right? We're just sort of focused on making the wealth big, and the wealth can be computed without x star. Nevertheless, via some sort of mathematical magic, at the end of the day, we get a regret bound that does depend explicitly on the unknown value x star. And that's why this is sort of a nice framework for building these algorithms, because we don't have to think about x star while we're building the algorithm. So there's one restriction here, is that we're not allowed to borrow money. So you're never allowed to bet more money than you have in your pocket, which means mathematically that xt is beta times wealth, where beta in minus 1 to 1 is called the betting fraction, because it's the fraction of money that you bet. This seems like it might be some sort of restricted special class of algorithms, but it's actually not. It turns out that it's just a different way of looking at algorithms. Any algorithm that's going to guarantee constant regret with respect to the origin here actually has to have the form of a betting algorithm. It's just that, other algorithms that are not explicitly written as betting algorithms, it's not clear from the pseudocode of the algorithm what the betting fractions beta will be, but nevertheless, they have to exist. Okay, so what's our overall strategy using coin betting here? We're going to compute a near optimal fixed betting fraction beta star. So if we were to use this beta star for every round as our betting fraction, we would actually get a second order regret bound. On the other hand, this is sort of an unrealistic algorithm because we don't know what beta star is at the beginning of time. So then we have to do step 3 is to find a way to generate some beta t on the fly that do nearly as well as beta star. And step 3 is sort of the part where you might feel like this is going to be very, very difficult. But it turns out that there's sort of a simple trick that allows us to make this quite easy. Let's get started with steps 1 and 2. So in order to do this, we're going to compute the wealth. So we need some analytical expression for what the wealth is. Just write down the wealth at time t is the wealth at time t minus 1 plus the amount of money we made at time t. If we use the fact that this is a betting algorithm, then xt can be written as beta times wealth at time t minus 1. So we can write the expression this way and unroll this recursion for t rounds to say that the wealth at time t is the product from 1 to t of 1 minus beta times g. Whenever I see a product, I tend to try to take a log because products are complicated and sums are less complicated. So we take a log, and we get the log wealth is equal to the sum of the logs of 1 minus beta times g. Great. So now we would like to use this to identify a good betting fraction beta star. One could sort of fix beta t to be a subconstant beta here, differentiate with respect to beta, try to analytically compute the best beta star. That's a little bit complicated. So instead what we're going to do in this talk is I'm just going to give you a good guess that I've pre-computed, and we're going to verify that indeed its wealth is quite high. So here is a value beta star. It has some funky expression, but the thing to notice about it importantly right now is that its magnitude is bounded by 1/2. So we can compute the wealth or the log wealth just by applying the expression on the previous slide and use the bound of the magnitude of beta star and a Taylor expansion to show that this wealth can be lower bounded by this quadratic expression. Then we plug in our value for beta star to get this final expression, which can be sort of fairly quickly checked. This was the log wealth, so we exponentiate. And now notice this funny thing happened. Inside this exponential, the sum of the gradients showed up. So we can actually just define a function h, which is given by taking any input and plugging it into where the sum of the gradients showed up inside this exponential expression. Notice that h as a function depends on the sum of the squared gradients, but that's okay. H really only exists for analysis, so it's allowed to depend on whatever it likes. So we have this function h. Just by using the standard coin betting argument now, we can say that the regret is bounded by 1 plus the differential conjugate of h, which is order x star times the square root of sum of the gradients squared. So now we're doing pretty well. We found a fixed betting fraction beta star that guarantees a second order regret bound. How can we learn about this beta star on the fly? This part is going to be a little bit of a sort of cute trick in some sense. So I'll call this online learning inside online learning, which is sort of, I think will be clear why in a minute. So we're going to compute the gap between the log wealth we obtain and the log wealth of beta star. So this is just, if we call wealth star the wealth of beta star, we just apply our log term. And now I'm going to do some algebraic trickery. I'm going to define this loss LT as minus log 1 minus beta g. And just by definition, now I can rewrite this expression as LT beta t minus LT beta star. And this is very interesting because this expression here looks a lot like the regret of picking beta t on the losses LT with respect to the comparison point beta star. And so now there is this notion of online learning inside online learning. I could choose my way of picking beta t as itself an online learning algorithm on the losses LT. The only problem is, now I have to maybe have to tune a learning rate for this online learning algorithm, and so I haven't really solved the problem. Fortunately, we can appeal to a different property of LT. Not only are they convex, they're actually x-concave. This means that the optimal learning rate here doesn't really depend on the value of beta star anymore. In this special case, we can exploit the x-concavity to use a different learning rate via the online Newton step algorithm, which will get us that the regret is actually smaller than square root of t. It's actually log t. And then using this, we can just unroll everything, say that the wealth is lower bounded by wealth star divided by t. So now we plug in our expressions for everything. Wealth is wealth star over t. We plug in our exponential expression. We get 1 on t times this exponent. And we redefine h as 1 on t times this times the value of the old h. Again, we can take the differential conjugate, and it turns out that this 1 on t extra term here doesn't make a difference. So we still end up with the second order bound. 1 on t, of course, has to make some difference. So what does it change? It changes the log 1 plus x star root t to a log 1 plus x star just t instead, basically. And the intuition behind why it's making such a small difference here is because this is an exponential thing, so it's growing much faster than this merely polynomial decay here. All right, so we did it. Let me just put all the pseudocode here together in one algorithm so that you can see it's actually surprisingly straightforward, even if our analysis took several pages. So we start with a betting fraction of 0 and a wealth of $1. Every round we play our bets by just taking the betting fraction times the wealth. We get the gradient GT and define this sort of fake loss LT of beta. We want to run gradient descent on beta, so we compute the gradient of LT, which we compute analytically. And then we set beta t plus 1 by gradient descent. So we take beta t and subtract zt times this learning rate. And this is sort of a different special learning rate that's exploiting the fact that these functions are x concave. And that's it. This algorithm will guarantee the second order regret bound that we were looking for. All right, so now that we're armed with the second order regret bound, we can show how to accomplish some interesting things. So first, we'll find a bound that depends on the sparsity of x star. Then we'll adapt to smoothness. And then finally, we'll adapt to strong convexity. Now, the rest of this talk will be hopefully a little bit less dense in details. I think these applications show sort of the power of these types of regret bounds, and that we use the algorithm almost as a black box to get some interesting things. All right, so first, sparsity. Remember in the previous section, we talked about how to get d-dimensional algorithms from one-dimensional algorithms. One approach is to use per-coordinate updates, which are sort of the same thing that Adagrad does. So we take the linear regrets, can be bounded by the sum over the dimensions of the sum of some one-dimensional regrets in some sense. So on each coordinate, we run an independent copy of the learner, which means that our regret will be the sum of their individual regrets. Now, if you work through the log factors here carefully, we'll pick up a log d factor, but otherwise, everything is going to be the same. In contrast, what happens if you use a gradient descent like Adagrad type guarantee? Then instead, you have to tune the learning rate to the maximum value of all of these individual coordinates. So you end up with sort of an infinity norm bound, where these inside the sum terms have come outside the sum at the expense of becoming their max. So what is the advantage of this per coordinate bound? Well, if the optimal point x star is sparse, say that many of the coordinates are 0, then let's say also assume for simplicity that its infinity norm is bounded by 1 and it's S sparse. Then we can just plug and chug the equations to show that this norm of this GT squared here is bounded by the infinity norm of gradients. So this whole thing is bounded by the 1 norm of x star times the square root of the sum of the squared infinity norms of the gradients. And if you like, you can also bound this by S times the square root of t. So depending on your mathematical aesthetics, you may prefer this bound or this bound, but either way, it's clear that we're getting some gain when the x star is sparse. You might think that we lose something for this, but it turns out we actually are surprisingly not losing much. So if we consider just the L2 norm bound that we would have liked to have gotten originally, perhaps, then we can again just write down this regret bound and now apply Cauchy-Schwarz. And it turns out that this is also bounded by the 2 norm of x star times the square root of some of the 2 norms of the gradient squared. So we really lost nothing. We still have this adaptivity to dense things, even though we also have some nice behavior when x star is sparse. I should note that both of these properties really leverage the automatic activity to each individual xi. Right? We're really using this auto-tuning in some sense of the algorithm here. And for this Cauchy-Schwarz argument, we're also using the fact that it's second order. We had to get that better bound in order to use Cauchy-Schwarz here to get the 2 norm of the gradients. Finally, one other caveat, this type of approach does not actually identify which coordinates of x star are 0. Instead, it's saying that your convergence rate will be just as good as if you had known which coordinates of x star were 0 ahead of time. So let me remark on sort of a similarity between these bounds and what happens in the expert setting. So the learning with expert advice is a special kind of online linear optimization in which we have to constrain all of our predictions to the probability simplex. And there's a really long history of parameter-free algorithms in this case, starting with normal hedge and containing many references that I've listed on this slide. In this special setting, because of the constraints, you can do some sort of interesting things, as well as the problem being in some ways sometimes a little bit harder. So for example, one of these bounds you could get is the squint algorithm, which obtains this following bound. Notice that it has the norm of x star, this unknown value, inside the bound, but it also has xt, the predictions made by the algorithm. Now, if you like, you may feel that, oh, I don't like seeing xt on both sides of the equation, so you can do some sort of algebra to show that this also implies a bound that looks quite a bit like our second order regret bound. The difference, though, is that it has this norm of absolute value of gt instead of gt squared here. However, in payment for this difference, it works inside the simplex. The bounds we were talking about in the previous slides are all unconstrained. It's not actually clear how to make them work inside the simplex. If you, in fact, as far as I know, it may not be known how to get the squared here while constraining yourself to the simplex. So there's some interesting gap. Okay, so let's move on to talk about smoothness. So here's a loss that is not smooth. Smooth losses just mean that there are no funny kinks. The loss is always kind of a smooth ride. Formally, smoothness means that the second derivative is bounded above by some L times the identity. We'll also assume that our gradients GT have some bounded variance sigma squared. And in this case, it turns out that the optimal learning rate for gradient descent is a little bit different. It depends on L and sigma, and it achieves an improved convergence bound that is L times the norm of x star squared over t plus sigma times the norm of x star over root t. This is better because with small sigma, we've improved the root t to t, and in general, sigma is smaller than g, so we should expect to see this to be a better bound. But we would like to be able to attain this without having to tune to the unknown parameters L and sigma. It turns out that our second order regret bound already does this. So we'll see that we get this just basically for free. In order to see the argument, we're going to have to look inside the online to batch conversion, and we're going to have to use the following property of smoothness, which is that the sum of gt squared, the gradient at xt squared, is the variance, plus the suboptimality f of xt minus f of x star. This is just a standard consequence of smoothness. All right, so what's the whole argument? In online to batch conversion, we looked at the suboptimality and bounded this above by a linear function using convexity. Then we can say that this linear function can be bounded using the regret bound. And we push the expectation inside the square root using Jensen inequality. Now we apply smoothness to see that this gt squared can be bounded by suboptimality plus sigma squared. And now something sort of magic has happened, because this expression has shown up on the left and the right-hand side of the equation. So I can solve for it just by quadratic formula. And now we use Jensen inequality again to recover exactly the stochastic gradient descent bounds up to log factors and constants. But we didn't have to do any tuning. Something sort of magical happened in this step 3 here, where even though the original algorithm knows nothing about L and sigma a priori, just by dint of the fact that it got a second order regret bound, we're able to just introduce L and sigma in the analysis without the algorithm knowing about it. Okay, so now we're adapting to smoothness very well. Let's talk about strong convexity. So what is strong convexity? Strong convexity is kind of the opposite of smoothness in some sense. Smoothness says that you don't have kinks. Strong convexity, but you might change kind of slowly. Strong convexity says that you grow very fast. So formally, you're saying that the second derivative, instead of being upper bounded, is lower bounded by some mu times the identity. And again, with gradient descent, with a different learning rate, you can get a much better convergence rate here. So if your learning rate is 1 on mu t, you can get a convergence rate of log t over mu t. But in order to do this, of course, you require to know the parameter mu. We'd like to not have this. This is possible. So it turns out that the metagrad and the related Mahler algorithms both obtain regret bounds that have this sort of following slightly different form, where it's the norm of x tar minus xt squared times gt squared, and then take the square root. If xt happened to be 0 all the time, this would be the same as the bounds we've seen previously in this section, but it's a little bit different because xt is inside the bound. It turns out, perhaps surprisingly, this actually implies adaptivity to strong convexity without knowing anything about the parameter mu. I'm not going to show you that exact argument here, but instead I'm going to look at a simple trick that allows us to obtain this style of bound using parameter-free algorithms. I think this trick also gives a nice intuition behind why we should expect the resulting algorithm to do better on strongly convex losses. All right, so in order to see how this works, we're going to think a little bit about the dynamics of our iterates xt. Remember that our error is norm of x star g over root t. So what this means is that if x star is quite big, then we might expect to move around a lot more. Right? We have sort of more room to make error, and so our iterates xt might be a little bit less correct. So pictorially, if x star is equal to 0, we say that the iterates xt are clustered closely around the origin, right? Because we're not allowed to have too much regrets, not allowed to have too much error, so we can't move too far. On the other hand, if x star is further from the origin, we might start at the origin and then kind of work our way out to the right dynamic range and then kind of be sort of sparsely or diffuse around x star. The right idea, but not quite as tight. We would like to get the best of both worlds, right? We start at the origin, we have to move to where x star is, but then we again cluster tightly around the correct value. Can I do this? Well, let's see one sort of approach that might give us some way to get it. So remember again that we get suboptimality norm of x star g over root t. The approach we're going to suggest is just to shift all the outputs by some constant v. So we pick some vector v, and whenever we try to play xt, we'll instead use the iterate xt plus v. If that happens, then that's sort of like shifting the origin to be at v. So instead of our convergence rate depending on norm of x star, it'll depend on norm of x star minus v. If v happened to be close to x star, this is of course way, way better. On the other hand, this doesn't really solve the problem, right? How do I find a v that's close to x star without knowing what x star is, right? That's sort of, a chicken and the egg type problem here. This is where we're going to have to use strong convexity. So before, we typically just use this linear approximation. With strong convexity, we can take advantage of a different property, which is that points with low error are necessarily close to the optimal point x star. This is not true if your function is not necessarily strongly convex, but if it is strongly convex, then once you have low error, you're close to x star. Okay. So how do we use this property? It turns out, right, that the average iterate already has small function value. Without doing anything, even if we set v is equal to 0, we're still going to converge. So we'll still have small function value, and so it must be close to x star. It might not be quite as close as we would like it to be, but it's closer. So maybe we can try using a running average for v. So the entire approach is like this. We say some parameter-free algorithm that gives us some x hat, say t. Then instead of playing x hat t as it is, we're going to add an offset. So the offset is a running average of all the iterates we've seen so far. Now, according to this intuition I've described here, maybe you should use the true running average, and that works fine. But it turns out if you work through the analysis, it's a little bit tighter to use this weighted average here that I've written here. So really, this is what I'm going to write as the recommended thing to do. And if you do a little bit of algebra here, you can prove to yourself that this bound will actually imply a metagrad-like regret bound, which does imply the 1 on mu error in the strongly convex problems. So what happened here? We sort of add the average, which gives this kind of nice virtuous cycle effect. As we get closer to as we have lower error, our average value will be closer to x star, which means that we have smaller error, which means that our average value is closer to x star again. We have this nice cycle that builds up when the function is strongly convex. This works for any parameter-free algorithm. We're really only relying on the fact that we had smaller regret when we're close to the origin. That's all we really needed here. Not only that, the algorithm actually is independent of mu in some sense, right? We didn't actually need to take mu as an input. It just kind of shows up magically in the analysis. All right, so finally, let's talk about the value of g. So in this talk so far, I've been assuming that g is equal to 1 for simplicity. And in practice, maybe it's not 1, but you can scale the gradients by, say, the largest upper bound for g you've seen at the first few gradients, and that'll probably make it effectively 1, just because gradients tend to decrease over time in any sort of reasonable setting. On the other hand, let's actually look through what happens if you keep track of where g is being used in these regret bounds. So we look at the regret. It's upper bounded by norm of x star times square root of g squared plus the sum of all the gradients squared. So when this is 1, I sort of just dropped it inside the big O, but in general, this is the final bound. What this means is that g is actually pretty robust, right? We can overestimate g by a factor of square root of t, and we'll lose only a constant in this regret bound, right? We can be quite conservative with what G is. In contrast, if we were to use the sort of standard gradient descent type approach, then we would, instead of having a value for G, we would have a value B, which is a bound on the norm of X star. Already, this is kind of a little bit annoying because it's harder to get some good idea for norm of X star ahead of time. But even worse, the bound is B times square root of sum of the gradients squared, which means that if B is wrong, you pay linearly, right? If B were off by a square root of T factor, you would have linear regret. Okay, you might say, but what's the worst case thing? Like truly, I know nothing. I might be, if I tried to say, oh, I think G is this, I'm going to be off by like T to the fourth or something like that. What can we do? If we don't know anything, then it turns out that there is a penalty that you pay. So the worst case bound is norm of X star G root T plus a penalty G times X star cubed. I'd like to point out, though, in this penalty that this norm of X star cubed does not depend on T. So the asymptotic performance is actually the same. As T gets big, you'll be looking at a norm of X star G over root T convergence bound. Not only that, it's actually seems likely that this is not perhaps a real bound. In the sense that the lower bound here is really relying on sort of the adversarial nature of the online learning problem. Whereas in a real stochastic environment, I've never seen the types of behavior that would allow such an adversary to exist. However, the bound is known to be tight. So we can obtain an upper bound that matches this lower bound exactly by lying to our algorithm. So we feed it a gradient GT that's sort of been clipped to have its norm be at most the maximum of all the previous gradients. And doing this with a little bit of work, you can obtain a bound that matches this. All right, so let's summarize what we see here. We built a parameter-free algorithm via a little bit of elbow grease and some trickery. And once we did that, it was possible to do some surprising adaptive extra results. We could do better when functions were sparse, do better when there was smoothness, we did better when there was strong convexity. And finally, we discussed a little bit the properties of unknown G. All right, so that's the end of this section. The next section, we're going to talk a bit about actual implementations and some empirical results.